Let us look at an example of artificial neural networks. Artificial neural networks are one of the current hype topics in machine learning and artificial intelligence, especially if we then talk about deep learning, deep artificial neural networks. Here's an example of a typical task which can easily be solved with an artificial neural network. It's basically the hello world of machine learning, meaning a very simple program which many people who learn machine learning start with and do their first exercises. It's about detecting handwritten numbers. What you see here are many handwritten numbers, 90881325 and so on. So for us humans, rather easy to understand, rather easy to read. In the first years of your life you learn that, but everyone watching this video now will be able to detect these numbers. But then describing to a computer how to do that, how to recognize this handwriting, even if it's only 10 different digits, is rather complex. Look at these. I mean, the 8s are written differently or pick out different fours. There's no one exact style what each of them looks like, but handwritings are different. And sometimes there are some parts of the image missing or so. So it's really difficult to write down exact rules how to do that. But machine learning can easily solve that problem and learn a model which can then detect handwriting. Now what can that look like? First, you need input data. You need to supply to this artificial neural network for the network to calculate the outcome, basically a digit from 0 to 9. And the input in this example is very simple, small pictures. So 28 times 28 pixels with gray values. Here we see a 9. It's a little pixeled. That's because we have a very low resolution. That's to keep the example simple, to keep the input layer simple. The input layer, that's a set of neurons. Here we have 784 neurons, so not the real neurons like you have in your head, but artificial neurons in this artificial neural network. And why do we have 784 neurons in this example? Well, because the image has 28 times 28 pixels. That means it has 784 pixels. And for the ease of implementing it, we attach each pixel to one neuron. So if you go through the pixels line by line, the uppermost left pixel is pixel 1, the next is pixel 2, and so on, down to the down corner on the right hand side, pixel 784. And you supply this gray value going from 0 to 255, so that's the number range, 0 to 255, to each of these different 784 pixels. That's the input layer of our artificial neural network. Well, if there's an input layer, you can already guess that there are other layers. Here we have the next layer, and in this example we have there 512 neurons. It's really difficult, it's an art to know what the optimal design of that network looks like. We'll come to that towards the end of this video. So for the moment, just take it for granted that there's a next level, and then we have either the same number or a different number of these artificial neurons. In this example, we have 512. And they are interconnected. So nodes, neurons in the input layer are connected to neurons in the next layer, but not among themselves, so not in the input layer among themselves. That's why we talk about different layers. And here in this example, we have them fully connected. Each of the 784 nodes in the first layer is connected to each of the 512 nodes in the second layer. And we don't only have the second layer, we might in this example have two further intermediate layers. So with the input layer, we have a series of intermediate layers, and you see it, as you see it here, in this example, these intermediate layers become leaner and leaner from 512 to 256 to 128 neurons. And then we have the output layer, in this example with 10 neurons, and they for us represent the outcome, the 0 to 9, the 10 different digits, which can be the result. Now this is the high-level structure of an artificial neural network. It has multiple layers, at least input layer and output layer, probably and typically intermediate layers, and in each of these layers it has these artificial neurons, and they are connected to the ones in the next layer. And now in such a neuron, and I put it in parentheses here because I said it's an artificial neuron, it's no real biological neuron, well, it has an activation function which transforms a set of inputs to an output. And typically the set of inputs is the sum of inputs. So if you think about the uppermost neuron in the first intermediate layer, it's connected to 784 neurons in the input layer. And now each of these input layer neurons sends a signal via this connection to this first neuron in the first intermediate layer. Now this first neuron has to think about, definitely an artificial neural network can't think and this neuron can't think, but it has to forward some signal to all the neurons in the next layer. And the question is, what signal should it forward? For this, typically, it sums up all the inputs and then it transforms them with an activation function. That's mimicked after how the neurons in our brains work with electrical impulses which reach these neurons and then they are either activated or not. And now the question is, what should this activation function be? Well, there are many different ones you could use, but only the nonlinear activation functions are the interesting ones, because only nonlinear activation functions allow you to compute non-trivial problems. So if this would be linear, if it's only the identity function, so f from x is x, then it would be pretty boring. Then you wouldn't have to span out this networks and it would all collapse to just a single layer. So only with nonlinear activation functions, you can solve complex nonlinear learning tasks. So 3 exemplary activation functions. First is the identity function, which I just named. Well, that's a linear function, so you can use it, but then it's not really worth putting up this effort of this neural network structure. And it's rather simple and you can only solve simple problems. For example, this handwriting problem you couldn't really solve with a linear activation function. A very prominent one is the logistic function. It's also known as sigmoid or soft step function. So it's this S-shaped function. And then another prominent one is the rectified linear unit, ReLU for short, which is basically the maximum of 0 or x. So meaning if the input is negative, then the output is 0. If the input is positive, then the output is the same as the input. It equals the input. And now it would go too deep in this short video here to explain you the differences between the different activation functions and provide you the rules how to choose one or the other. That's a very big topic for somebody really operating such learning algorithms, designing such learning algorithms. But here for the moment it should suffice to know that there is something like this activation function in these neural networks. And now if you provide a picture like this small 28 times 28 pixel gray values to that, you see here the input layer, the different gray levels, and then it moves on to the intermediate layers. And these intermediate layers somehow learn by adapting the weights. So before I said that these layers are interconnected with each other. These are the black lines you see on that chart between the different neurons. But these lines can also have weights. So typically you start with all of them having the same weight, but then the learning takes place by adapting these weights, by making some of these links between neurons stronger and making others weaker. And thereby this whole network, and especially these intermediate layers, somehow learn to represent the inputs in a way which helps them compute the outputs. And in the image processing, what typically is the assumption, what happens in this learning in these intermediate layers, is that you learn first abstract features such as edges, and then later on in the intermediate layers you also learn shapes, like for example a circle or so on. So in a way the system learns to detect things which we as humans also know and detect, but it's not fully mimicking how we learn, how we recognize these images and the digits in these images. And then it moves on to the output layer, and here in this example, well, the neuron representing the 9 is activated, all the others are not, and with that a computer program running this algorithm, this artificial neural network, knows then that it should compute with a 9. So if you want to learn more about this, you might want to visit this tutorial we link here. There you see the exact computer code, how to implement this example and run it, and there you get a lot deeper understanding of what I've just been describing to you. But now you might think, well, do I need artificial neural networks, deep learning for detecting numbers from 0 to 9? Well, as said before, this is a simple hello world example, a very simple stylized example to get a first feeling on how that looks like. And obviously, in most real-life applications, you apply it to way more complex problems. Just to show you one more complex problem, what you see here is an image recorded by a regular camera in a low light situation and then processed traditionally. And you can hardly see, if at all, what's displayed on that image. And I think we all know this problem, taking a photo in too low a light and then having a really bad quality of that photo. Obviously, you could have a longer duration for taking the photo, more light would come to the lens, to the sensor, but then you might shake your camera and the image would be blurred again. So oftentimes there are situations where you can't take real good photos. Now the question is, what can artificial neural networks, deep learning, help us to improve that? Well, there were researchers who trained a full convolutional neural network, probably you don't know yet what that means, on a data set of raw, short exposure night images with corresponding long exposure reference images. So they made 2 images of the same situation, and this of many different situations, and then they took this as training data, as basically labeled data. They had the short exposure night image, the dark image, and the better long exposure image, and then trained an algorithm to calculate from the bad image the good image, from the short exposure night image the long exposure reference image with high quality. And they found out that this efficiently yields enhanced results from extreme scenarios such as night photography. Here's an example from them where you then can way better see the different items on the photo. And this is something, again, which would be probably impossible to really do in a high quality with traditional computer programming, but with machine learning you can achieve these stunning results. Now, before I said to you that it's a question which activation function to use in the neurons. Well, that's only one of the many design decisions you have to make if you decide on how to build an artificial neural network. What you see on this chart are many different types, the whole variety of different neural network, basically architecture. So you have very simple things like the perceptron on the upper left, just 2 input neurons, 1 output neuron in that example, irregular feed forward or feed backward neural networks. But then you also see these more complex structures there, the deep convolutional neural networks or generative adversarial networks and so on. And it would go too deep here to explain for each of these what the typical application scenario is. What you should understand is that there are many different architectures how you can set up this type of algorithm, these artificial neural networks. And then obviously there's more of these types than you see on this chart. And even if you know the general types, the general structure, you still need to decide on the number of layers, the number of neurons per layer, and so on. So there are very many design decisions to take when providing such a neural network for a specific application scenario. And with some experience, then the experts in this know which type of network to take, which architectures, which number of layers, and so on typically work well. But then also it's a trial and error process where you try it out and see whether changes in the architecture, the number of layers, the number of neurons, the activation function, and so on, improve or decrease your performance. And then it's a mixture of an art of knowing what's good there and of trial and error process for finding a real well-performing model.